Hello, today I'm going to talk about the traditional square of opposition and the modified Venn diagram approach to testing immediate inferences of categorical propositions. Now, if you start with what we already knew, that the modern square of opposition has on it only contradictories. Remember, by the modern square of opposition, if the A statement is true, you know that the corresponding O statement is false, which makes sense if you think about the Venn diagrams. All S are P for an A statement, all S are P, everything that's inside of S, areas 1 and 2, all of them are inside of P, so they're in area 2. That means that area 1 is shaded. Whereas some S are not P, an O statement, that means there's at least one S, so areas 1 and 2, there's something in there. There is at least one of those, and it's inside, or it's not inside of the P area, so it's inside of area 1. So you have an X in area 1. Now, if this is true that there's nothing in area 1, then this has to be false that there's something in area 1. And similar things can be set up here. No SRP tells you there's nothing inside of S, there's nothing in 1 and 2. That's also inside of P, so area 2 gets shaded. And then some SRP, there's at least one S, so there's something in area 1 or 2, and that S is inside of P, area 2. Okay, so if the E statement is true, the I statement has to be false. There's nothing in area 2 here. There can't be something in area 2 here, and vice versa. Now, the traditional square of opposition adds 3 more operations, though. 3 more relationships, technically speaking. Those relationships are contrary, subcontrary, and subalternation. And subalternation applies to both sides here. I just didn't write it out on both sides. The ideas are basically these. The contrary relationship says that if at least one of these has to be false. So if one of them is true, the other has to be false. Now they could both be false. That's a possibility. So if one is false, that doesn't tell you anything about the other. But if one of them is true, because at least one has to be false, the other one is going to have to be the false one. So if the A is true, you know that the E is false. Now, subcontrary. Here, at least one of them has to be true. So if one of them is true, the other one may or may not be. But if one of them is false, you know that the other one has to be true. Now, if you think about this, this makes sense, right? So think about the subcontrary first. If there are, now let's see, this is the important part. If S's do exist, they have to exist in either area 1 or 2. Well, this one says they exist in area 2. This one says they exist in area 1. They've got to exist in one or the other, so at least one of these has to be true. And this up here, if there are no S's, then it's possible that there's nothing in area 1 and there's nothing in area 2. But as long as S's exist, and that's the key part here, as long as S's exist, then they've got to either exist in area 2 or in area 1, which would mean one of these is going to have to be false. If they exist in area 2, that means this one has to be false. If they exist in area 1, that means this one has to be false. Okay? So that's contrary and subcontrary. Subalternation is just carrying some intuitions forward that you probably had already. That if an A statement is true, the corresponding I statement has to be true. Truth flows down. That's subalternation, or part of it at least. Because if S's exist, and this is the key part, if S's exist, they have to exist in either 1 or 2. Well, this says they don't exist in 1. That means they're going to have to exist in 2. Over here, truth flows down. If S's exist, then they have to exist in 1 or 2. Well, this says they don't exist in 2, so they have to exist in 1. And that's what this one says. Now, by the same token, you can flip this around. If this is false, that's going to guarantee that this is going to have to be false too, if S's exist. Because if S's exist, and it's false that they exist in area 2, then it has to be false that they don't exist in area 1. And the same thing over here. If it's false that S's exist, then if they don't exist here, I'm sorry, let me back up here. If S's exist, sorry about that, if S's exist, and it's false that they exist in area 1, then they're going to have to exist in area 2. So if this is false, this is going to have to be false also. So there are your relationships. Now you can prove these using the Venn diagrams with a modified approach. Notice, if S's exist, okay, if there actually are S's, but they don't exist in area 1, they're not existing there, then they have to exist in area 2. So you put an X with a circle around it. Now, without that X with a circle, this bottom one says there's an X in area 2. Without the X in a circle, there wouldn't be anything in area 2 up here. So this does not guarantee this. But as soon as S's exist, you put an X with a circle in area 2. Now, is there something in area 2 up here? The answer is yes. So everything that's down here is already up here. Every mark that's down here is already up here. So this is what we call conditionally valid. A, if it is true, is going to guarantee that the I is true on the condition that S's actually exist. Now you may have to repeat that part, and if so, back it up and redo it. Same thing over here. If you just go with the Venn diagrams as they are here, no S or P, does that guarantee that there's something that's in S that's not in P? Well, no, because notice there's an X in area 1 here, but not here. But if S's do in fact exist, they have to exist here. Right? Because it's already saying they don't exist in area 2, so they have to exist in area 1. Now, is everything that's down here an X in area 1? Is it already up here? Yes. So if this is true, that's going to guarantee that this is true. That's subalternation. Now, back to the top here again, the contraries. Notice at least one of these is going to have to be false if S's exist, because they have to exist in either area 2 or in area 1. So, you can see it in these Venn diagrams. If this is true, that there's something in area 1 and nothing in area 2, then it has to be false that there's nothing in area 1 and something in area 2. And vice versa. Now notice they both could be false, right? It's at least possible there's something in area 2 and in area 1. If there's something in area 1, then this is false. If there's something in area 2, this is false. So that's a possibility, right? Now down here, they can't both be false. The reason they can't both be false, at least one of them has to be true, is if S's exist, they have to exist in area 2 or in area 1. This one says they exist in area 2. Well, if it's false they exist in area 2, then they're going to have to exist in area 1. So this one's a little bit easier to see, the subcontrary. But that only makes sense if S's exist. So so these are conditionally valid operations. So that's something to keep in mind here. Subcontrary, subalternation, and contrary are all conditionally valid. They are valid on the condition that S's exist. Now, how does this play out with immediate inferences? Well, let's get a couple of examples here. Suppose we start off with this. All T R L. Therefore, some T R L. Now, never mind that my letters are different now here. I'm just trying to come up with examples that you might get after you symbolized, like all teachers are leaders in the community. Okay, I kind of like that one. Anyway, if all teachers are leaders in the community, then certainly some are, because teachers actually exist. Now, this is valid on the condition that teachers exist. And the reason this matters is because notice that some means there is at least one. There is at least one teacher. There exists at least one teacher. And again, if this is true, then this can be guaranteed on the condition that teachers exist. If teachers don't exist, this is invalid. It commits the existential fallacy. If teachers do exist, it's valid from the Aristotelian standpoint alone. Now, I'm going to add something here. Sorry to bend down to pick up my handy dandy rag here. Let's think of a different example here. Take a look at an example. Let's say you had this. It is false that some T are not L. Therefore, some T are L. Now, immediately, I hope you notice that that's a false O statement, which makes a true A. And we already said if you have a true A, you get a true I. But let's just go through it just to be clear. If this is false, by subcontrary, they can't both be false. At least one of them has to be true. So if the O statement is false, the I statement is going to have to be true. This is going to be conditionally valid. On the condition that T's exist, this is valid. Suppose we change it, and instead of having, suppose you have this. Take the is false that off of there. And we change it to this, some T R L. Now, this says there's at least one T that's not an L. Does that guarantee that there's a T that is an L? Well, no. This just says at least one of them is true, and now this meets that condition. Since this meets the condition that at least one is true, it doesn't guarantee that the other is going to be true too. Okay? Other examples. Let's say we did this.